Hello, and welcome to rational functions. I know you've had some exposure to rational functions, but we want to look at something that you may not have seen before. So let's look at the graph of these two rational functions, f and g. When I first look at them, I think, wow, they're the same. But then I notice there's one slight difference on the graph of g. Now, if you put these into a graphing program, they would look exactly the same, okay? They are not able to draw the holes in the graph, as you can see on the graph of g, okay? So how do we find the location of that hole? I had to find the location to make the graphing program put the open circle there. So how would we do that? So let's first talk about domain of a rational function. We talk about domain of functions all the time. So what are the real numbers that I can put into f that will produce real numbers for function values? Well, we know that a rational function, we always say the domain is all real numbers except any real number that makes the denominator 0. So the zeros of the polynomial in the denominator would be the places where the function would not be defined, or at the values it's not defined. We've previously talked about continuity, and we talked about a function is continuous if you can trace its graph without lifting your finger or pencil. I cannot do that on either of these graphs. There is a break in the graph. All right, so let's talk about the domain of f. What real number would make the denominator 0 would be -2. So I like to write it like this. Just for now, x cannot be -2. So that's the one thing we kick out of the set of real numbers. Now, and I know in college algebra, you're trained to put domain in interval notation all the time, which is great, but I don't need it always. It's not that user-friendly for what we're talking about now. So I'm going to talk about it as in what are the values that are not in the domain. And what we say is anything that's excluded from the domain produces a discontinuity, a place on the graph where the function is not continuous. So what's happening at -2 on the graph? Well, we've talked about vertical asymptotes, so we've got this imaginary vertical line that the graph does not touch or cross, but it approaches that line from both sides. So this function has a vertical asymptote, which is a line x equals, where does it cross the x-axis? At -2. So when you give a vertical asymptote, you give an equation because it is a line. All right? Okay, so when I go to g, let's talk about g. What are the real numbers that make the denominator 0, or the zeros of this rational function? Well, we've always thought if we can factor it, it's easy to find the zeros because we know how to find zeros of a factor. So this is a difference of two perfect squares. So it factors into a sum and a difference of the same two terms. Okay, so here I can see that my domain is all real numbers except for -2 and 2. So those are the real zeros of the denominator. So it's very similar to the graph of f. There is a break in my graph here. I have to go from the curve on the left to the curve on the right. I have to pick up my pencil, jump over that imaginary line, and to get to the other curve. So we say it does have a vertical asymptote, so it is discontinuous at x equals -2, but it is also discontinuous because there is a break in my graph here. This is what we call a hole in the graph, or more official name would be called a removable discontinuity. So these are both discontinuities, places where the function is not continuous. A hole is called a removable discontinuity because, I'll show you why. And when you get to calculus, you'll talk about that, you'll use that terminology quite a bit. Okay, so why is it called a removable discontinuity? Well, when I look now, after my denominator is factored, I can see that I have a common factor. x minus 2. Well, x minus 2 is the factor that produces this discontinuity at 2. So why is it removable? Because I can divide that out of the numerator and the denominator, and it is gone. I have now created a function 1 over x plus 2 that is continuous at 2, which is over here. Notice how these are the same now. Okay, and this one is continuous. There is no hole there at x equals 2. So that's why it's called a removable discontinuity, or the quick, fast way is a hole in the graph. So that's why these two graphs are almost exactly the same. The only thing different about them is that g, my function g, has a hole in the graph at 2, whereas the function f does not. So the good thing is, if we were going to graph this function g, once we got rid of that common factor, we would use this right here to finish the graph, because it behaves the same as f everywhere but that location. Now, when I said, oh, how did I know where to put the hole? Because I am really smart. Ha ha, no. How did I find the y coordinate of the hole? I plugged it in here. So I said, okay, once my function is in lowest terms or simplified, 1 over x plus 2 is simplified, no common factor. Then I put that value, that x value, where the hole occurs, into that function, and that's where I get the y coordinate of my hole in the graph, so that I can find that location and draw that open circle. Okay, because if I put it back up in here, I'm not going to get a number. It's going to make the denominator 0. Okay, so what we're interested in doing is figuring out these numbers that are zeros of the denominator, these discontinuities, what's happening. Is there going to be a vertical asymptote or a hole at each one? It's one or the other at each discontinuity. Okay? Let's look at one other situation before we do more of that. So here's our function h. Now, when I look at this, I look at the denominator, it kind of looks like the denominator in g in our last function, except for the fact that this is a sum of squares. It's a sum of two squares, which does not factor into real numbers, okay? But if we were thinking, okay, it doesn't factor, well, let's find the zeros. What's going to make x squared plus 4 equal to 0? Because those would be the values I exclude. Well, when we solve this quadratic equation, when I get here, I should realize there is no real number that I square to get negative 4. When I square any real number, it's positive. But if we don't catch that, we keep going. We apply the square root property, and we say x is the plus or minus square root of negative 4. Hopefully now you see it. Square root of a negative means it's not a real number. So you get x values that are imaginary, okay? When we're graphing, this is our xy coordinate system, or our Cartesian coordinate system. These are real number axes, okay? So there is no imaginary number, a place for imaginary numbers in this Cartesian coordinate system, in the complex system, but not our typical XY graphing system. Okay, so what does that tell me? There are no real numbers that make the denominator 0, so then we would say that the domain is all real numbers. It's all real numbers except real zeros of the denominator. There are none. Okay, there are no real zeros of the denominator, so the domain is all real numbers, which means this function is continuous everywhere. I can trace this thing without lifting my finger or pencil. Okay, so it doesn't have any vertical asymptotes. So there are no vertical asymptotes, which can happen. Rational functions do not always have them. All right. Okay, let's classify these discontinuities. Okay, so basically you have a sheet that tells you the steps, and you need to follow the rules. Okay, the first step says, factor the denominator to determine the domain. Basically, determine where are the discontinuities so we can decide what they are. Okay, so factor the denominator. First thing you should always try when you factor is greatest common factor. Please do not forget it. It's the first thing you've ever learned how to do, and for some reason it gets forgotten. Okay, so if I take out a 5, then I can see that x squared minus 9 is a difference of two perfect squares. All right, so the denominator's factored. Very easy here for me to see the zeros. Is 5 is a constant factor. It will never be 0. So it's not going to give you a 0. So it's only variable factors we're looking at. Okay, so we can say then that x cannot be negative 3, whoops, and x cannot be 3. So I have, my domain would be all real numbers except for negative 3 and 3. And you could write that in interval notation. But these are it's discontinuous at negative 3 and 3. So I need to know, at negative 3, do I have a vertical asymptote or a hole in the graph? At 3, do I have a vertical asymptote or a hole in the graph? Okay, one or the other at each discontinuity. So now we factor the numerator because we're looking for common factors. That's what we're going to look for first. Do we have any common factors once the rational expression is completely factored top and bottom? Well, in the top, a nice little trinomial, no common factors, so I can go to this unfoiling method or whatever you call it. So it's x plus 2, x plus 3. Okay, so now look what happens. I have a factor of x plus 3 in the numerator, a factor of x plus 3 in the denominator. That will completely divide out. So that is what we call a removable discontinuity or a hole in the graph at the 0 of that factor. So here's what I've got remaining. Okay. So that tells me then that at negative 3, we have a hole in the graph. Okay. If I want to find the y-coordinate of that point, then I have to use my simplified function. So from now on out, you're going to use your simplified or your rational expression function in lowest terms to do everything from now on out. So if I want to find the y-coordinate, then I plug negative 3 into that new expression after I've divided out the common factor. All right, so we end up getting, negative 1 over negative 30, which is 1/30, I believe. Okay, so then if I was going to graph it, I would say, okay, the location or the ordered pair for the whole would be at negative 3, 1/30. So that's where I would go to graph that on my graph, put that on my graph. Okay, now once there are no common factors, this is what the book says, lowest terms. No common factors, whatever makes the denominator 0 now results in a vertical asymptote. So look at my variable factor, which would be a 3, would make that 0. So that tells me then that at x equals 3, at this discontinuity, I have a vertical asymptote. And it's a vertical line, x equals, and it crosses the x-axis at 3. Okay, so two discontinuities, one's removable, one is not. And then we go about doing all the rest of the good stuff to graph it. Okay, let's look at another example. Now, this is a tricky one. Okay, follow the rules. Rule number 1, find the domain. Factor the denominator, find the zeros of the denominator. Well, can't factor it, so I know that x cannot be 1. Now, if you want to write an interval notation for practice, we'll do one of these. So it's basically all real numbers from negative infinity to 1, not including 1, or from 1 to infinity. So I have a break in my graph at 1. All right, what's going to happen there? Do I have a vertical asymptote, or do I have a removable discontinuity or a hole in the graph? Okay, then step number 2 would be to factor the numerator, okay? Because we're looking for common factors. So when I factor the numerator, greatest common factor, all three terms do not have a common factor. So whatever method you use to factor these trinomials with the leading coefficient, other than a 1, everybody's got their own little method. I think that would be, oops, wait, no, hello. My bad, that should be a 1. And that should be a 2. Sorry about that. Don't use my method, clearly. There we go. Okay. Now you can see common factor, numerator, and denominator. Common factor of x minus 1, which tells me then at 1, I have a hole in the graph at x equals 1, because that factor will completely divide out. Now, here's where it gets a little crazy. What does that function look like now that I've simplified it or reduced it to lowest terms? 3x plus 2. That's not even a rational function anymore. Okay, a rational function needs to be a ratio of two polynomials. Technically, the polynomial in the denominator isn't considered to be a 1. So what kind of function is this now? It's linear. This is a line. Okay, so yes, it's a rational function, but these two graphs are going to be exactly the same, like we just saw a little bit ago, but our original rational function is not defined at 1, whereas this line, I can put anything I want into a line. So my graph is going to be a line with a hole in it, the graph of this rational function. Okay, so how do we find the y coordinate of the hole? We plug 1 into the simplified rational expression. So that becomes 3 times 1 plus 2. So f of 1 is 5. So the coordinates of the hole in the graph would be at 1, 5. Okay. Now, when you do these rational functions, you're going to continue on and say, what's the end behavior? What's the intercepts? Well, this one isn't even a rational function, so I don't even have to go through those steps. If I'm going to draw the graph of this, I know how to draw that. I know how to draw the line 3x plus 2, right? Oops, I don't want to do that. So it has a y-intercept of, okay, has a y-intercept of 2 and a slope of 3. So now I got to go back and fix this because it's supposed to have a hole in the graph at 1, 5. So wherever 1, 5 is. Just FYI, this is not drawn to scale. Okay, so this hole is at 1, 5. Okay, so this graph right here is actually the graph of this rational function. Okay, so the graph, let's write that down. The graph of f of x, x squared minus x minus 2 over x minus 1 is a line with a hole at 1, 5. Okay, so it's not your typical looking rational function graph. Fun, love those. You see those quite a bit in calculus as well. Okay, end behavior. The other thing we talk about with rational functions is what's happening at the ends. We know what happens at the discontinuities now. What happens at the far left and right end? So what we're wondering is, if we're looking at our graph, does the graph, does it level off and approach some horizontal line? So does it do something like this where it looks kind of flat? Okay, or does it possibly increase without bound, or possibly decrease without bound? I guess I shouldn't draw those all in the same picture, but what is happening at the ends? Okay, we know polynomials, they either increase without bound, decrease without bound, but our rational functions could have this a horizontal asymptote line that the graph approaches. We've talked about that. Okay, so these are the rules. Basically, you're comparing the degree of the numerator to the degree of the denominator. So these are the three different situations after you compare, you check. Okay, so here's three different rational functions. Yes, they look very similar. Look at f. All right, what's the degree of the polynomial in the top? The top is a constant, 4, so the degree is 0. The polynomial in the bottom, the highest power on the variable is 2, so the degree is 2. So here, the top is less than the bottom. So what happens when the degree of the top is less than the degree of the bottom? It does have a horizontal asymptote. It is the line y equals 0, or the x-axis. Okay, so degree of the top is less than the bottom, has a horizontal asymptote. They will be in the form y equals some number. Okay, so you can see as I go far to the right on my graph, notice how the curve is getting close to the x-axis. And same thing with the left. And if you recall, rational functions do the same. If they have a horizontal asymptote, it's the same on both sides. There are functions that are different that could have two horizontal asymptotes. You see those in calculus. All right, so h, degree of the top is 2. It's quadratic. The degree of the bottom is 2. It's also quadratic. The degree of the top is equal to the degree of the bottom. So when they are equal, then yes, it has a horizontal asymptote. It is the line y equals, what does this mean? A ratio of the leading coefficients. So it's the leading coefficient of the top over the leading coefficient at the bottom. Remember that leading coefficient means the coefficient on the term that has the highest power of x. So this is my ratio of my leading coefficients. So it's 4 over 2, which we would simplify that and say the horizontal asymptote is the line y equals 2, which we can see here on our picture. Far to the right, it's getting close to that line, and far to the left doing the same thing. So we draw these as dashed lines. They're guidelines to help us draw the graph accurately. Okay, in our last situation, R, degree of the top is 3 cubed. Degree of the bottom is squared again. Yes, it's in the same all the time. You're not seeing things. Okay, degree of the top 3 is larger than the degree of the bottom. So here's the situation right here. When the degree of the top is larger, then basically you have no horizontal asymptote. That's the thing. Okay, so there is no horizontal asymptote. But if the degree of the top is larger by exactly 1, 3 is 1 larger than 2. So that's this situation right here. Degree of the top is greater than the degree of bottom by exactly 1. Then it has what's called an oblique asymptote, or a lot of times we call it a slant asymptote because it's a line with a slope other than 0 like a horizontal asymptote has. Okay, if that top would have been a 5, and the bottom was a 2, then we'd say it has neither. It has no horizontal asymptote and no slant or oblique asymptote. So I don't know what happens at the ends. I've just got to plug in points. Plug in a big number, plug in a little number. Okay, so I can see then that this is my slant asymptote. It's the line y equals something. It will be in the form y equals mx plus b. So it's a linear function with a slope that is not 0. Okay, so the slope is not 0. Okay, this one, the y-intercept is 0, which is totally fine. I believe this is, well, we can tell, I can read that this is a 2 right here. So this is the line y equals 2x. Okay, now I also had to put that equation into the graphing program. So how do we find these equations of these slant or oblique asymptotes? Well, we'll talk about that in the next video. So stay tuned. Okay, and then notice none of these have a vertical asymptote. Why? Because the denominator does not have any real zeros. If we think about it, it's a sum of squares, so to speak. Okay, so it would have non-real solutions. So there's no vertical asymptotes in any of these. All right, let's do one, and let's put everything together. Asymptotes, holes, and we'll throw in intercepts for practice. Okay, so if you want to try this on your own, pause the video, go through the steps, and then come back and check your answers. Okay, so first thing you need to do is factor the denominator. First thing you should check for is greatest common factor. I noticed that all 3 terms have a factor of x. So when I factor that out, I get 2x squared minus 5x minus 3. And then this is one of those trinomials that if it's factorable, it will factor into 2 binomials using maybe AC grouping or trial and error. I'm a trial and error girl unless it's really big numbers. But that's because that's the way we learned back in the day. I'm not sure I even knew how to do AC grouping till I started teaching high school. Weird. Anyway, I believe that is going to work. Okay, so first thing, then next we need domain, or what are our discontinuities? Where is the function discontinuous? Well, this factor of x, what's going to make that 0? 0. So x is a 0 of the denominator. Oh, sorry, not x. 0 is a 0 of the denominator. What's going to make this factor 0? X is negative 1/2 is a 0 of the denominator, and x equals 3. So these are all the zeros, real zeros of the denominator, which means these are the places where my graph is discontinuous. So if I'm talking domain, I'm saying x cannot be any of those. And I don't want to write that in interval notation because I don't really need it. So what's happening at each of those discontinuities? Is there a hole or a vertical asymptote? So I have to decide at each one of them. Where do we go now? Numerator. Factor the numerator. I see common factor of x again. So x, and when I factor out an x, I get x plus 3. Okay, so now I look for common factors. That's the first thing I do. And I do have a common factor. I have a common factor of x. Okay, common factor of x, which will completely divide out. So the 0 of that factor is 0. So what's happening on the graph at x equals 0? There is a hole. Okay. Now, when I divide that out, I'm going to, well, you can see it there, but I'm going to come down here and rewrite it. So I have x plus 3. Now, you can either use the factored form in the bottom, or it depends what you're going to do with it. You might want to go back to the unfactored back here. If you were plugging something in like for the y-intercept, that's just personal preference. Okay. All right. So that's my function in lowest terms. So once you've divided out the common factor, you use this from now on out. Do not go back to the original. It's okay sometimes, but not all the time, so don't do it. Okay? All right. So what happens? Oh, I'm sorry. I didn't want to put that. Oh, well, it doesn't matter. I'll go here. So here I can see that that's these two, right? So I can see now in lowest terms, the zeros of the denominator are -1/2 and 3. That means at each of these there is a vertical asymptote. Okay? If there's no common factors, anything that makes the denominator 0 results in a vertical asymptote. So the hole in the graph, then that means I'm going to plug 0 into this function. That's where I like this version because it's easy to put 0 in here. 0 here gives me 3 on top. 0 here and here gives me -3 on bottom. So if you remember in a polynomial, the constant term was the y-intercept. In a rational function, the ratio of the constants will be the y-intercept. So that means f of 0 is -1. Okay, so the location of the hole would be 0, -1. Okay, where is that point located in the xy coordinate system? 0, -1. This is on the y-axis. The hole is on the y-axis. So what does that tell me about my intercepts? Right there, I know there is no y-intercept. If 0 is not in the domain, which it's not, right here, 0 is not in the domain, tells me there is no y-intercept. So I'm not even going to try and find that. Okay, what are my vertical asymptotes? They're the equation x equals -1/2 and x equals 3. So I have 2 vertical asymptotes and 1 hole. All right, now horizontal asymptote, oblique asymptote, or neither. So let's talk about end behavior, basically. What's going to happen far to the right and far to the left on the graph? I don't know. So compare the degree of the polynomial in the top. You can actually get that from up here, your highest powered terms. You can also get that from here. X in the top, I have degree 1. In the bottom, I have degree 2. Top is less than the bottom. So I do have a, whoops, not a slant, a horizontal asymptote, which is the line y equals 0 or the x-axis. Okay, if I went back up here, degree of the top is 2, degree of the bottom is 3, 2 is less than 3, same thing. So you'll be fine if you use that simplified expression. All right, now x-intercepts. The x-intercepts are the zeros of the function, but the only way a fraction is 0 is if the top is 0. So the quick way of finding the x-intercepts is once your expression is simplified, then all you have to do, and remember there could be more than one, all you have to do is set the numerator equal to 0. So the numerator, this is on your sheet also, equal to 0. So what's the value of x that makes x plus 3 0? Notice I want to go to the simplified because if I go to the original, I'm going to say that there is an x-intercept where there's a hole in the graph, and that's not cool. Can't be both. Can't be a point and not a point. All right, so I get x equals -3. So my x-intercept has an x-coordinate of -3. When I plug -3 into the function, I get 0. So the ordered pair is -3, 0. And then you put all that on the picture, and it looks so pretty. And there you have it. That's how we find asymptotes, holes, and intercepts. In the next video, we'll talk about those new asymptotes, oblique asymptotes.